Hi, welcome to Chapter 20, Part 2 on telescopes. We usually think of telescopes in terms of visible light telescopes or optical telescopes. And the two types of telescopes for this application are either refracting or reflecting telescopes. So a refracting telescope uses a curved lens to gather and focus the light. So in this diagram here, we can see the object, a candle far away, has light rays coming into the telescope, and the purpose of this convex or converging lens here is to focus these light rays to form an image. And the distance from the lens to the image is called the focal length of the lens, or the focal length of the telescope. Now, a more powerful type of telescope, because they can be made much bigger, uses a curved mirror instead of a lens. And so this is a reflecting telescope. Notice the surface of this mirror is concave, and it has the same purpose as the lens does here. The light rays from a distant object are brought together to a focus point right here to form an image. And so again, the distance from this image to the mirror is called the focal length of the mirror, or in our application, the focal length of the telescope. So all modern telescopes that are used by professional astronomers are actually reflecting telescopes. These mirrors can be made much larger than the lenses can. And by the way, the reflecting telescope was invented by Isaac Newton over 400 years ago. In addition to the primary lens here, or primary mirror in a reflecting telescope, there is also a secondary optic used to help magnify the image so that it's larger. So in the case of our refracting telescope, here is the primary lens up here. So the light rays are coming in. This lens focuses the light rays to form an image right here, and then another lens here called the eyepiece actually magnifies the image so that it's larger. In a telescope like this is a reflecting telescope. Here is the mirror down here. This actually has a couple of different secondary optics. Notice the light rays bounce off of the mirror, and instead of forming an image over here in front of the telescope, they are actually bounced off a tiny little secondary mirror and sent back through a hole in the primary mirror so that the eyepiece here can magnify the image down here. So what we're going to do next is talk about the three powers of a telescope. So telescopes basically do three things. They collect and gather a lot of light. So this is called the light gathering power. Telescopes also allow us to see details in the objects we're looking at. And so this is called the resolving power of a telescope, how much resolution it has. And then, of course, finally, a telescope, we want it to be able to magnify the image, because all of the objects that astronomers look at are very far away, so they're generally very small in the sky, and so the telescope has to also have magnifying power. So we're going to take a look at these three powers of the telescope next. The first and most important power of the telescope is actually the light gathering power. And here is an example where size does matter. The larger the telescope is, the more light it can collect. So if you think of a telescope like a bucket that collects rain in a rainstorm, the bigger the bucket, obviously the more water we're going to be able to collect. So if we think of light as photons streaming in from space, then the telescope is called a light bucket, or a photon bucket, to collect light. So the larger this diameter is here, obviously the more light we can gather in the telescope. So this telescope here has a larger diameter than the small one here, so it's going to collect more light. But remember, it's not just the diameter of the telescope, it's the whole area of this telescope lens or mirror that collects the light. So the lens or mirror is always a circle, and so remember from math class, the area of a circle is given by pi r squared. And r, of course, is the diameter divided by 2, right? The radius of a circle is half of the diameter. So this is the equation for the area of a circle in terms of the diameter of the telescope. So let's just look at an example here to see what we mean by light gathering power. So let's find the light gathering power of a 3-inch diameter or 76 millimeter telescope compared to the unaided human eye, which has a pupil diameter of about 8 millimeters. So what we're going to do here is we're going to compare the naked eye, all right, or the unaided eye. We're going to compare that to a small little telescope, the kind that you could buy for, much less than $100. You can get a 3-inch telescope. And we're going to find out that the 3-inch telescope is actually much superior to the unaided eye. So what we're going to do here is for light gathering power, we're going to look at the ratio of the area of the telescope to the area of our pupil. So we're going to use this equation here. So we have pi d over 2 squared, and down here we have pi d over 2 squared. So notice that the pi's cancel and the factors of 2 cancel, so all that remains is the diameter squared. So let's do it in millimeters. So we were told the 3-inch telescope is 76 millimeters. So on top we have 76 squared. On the bottom is the diameter of our pupil when it's night adapted, when our eyes are dilated, and that's about 8 millimeters. So on down here we have 8 squared. So 76 squared divided by 8 squared is about 90. So what does this number mean? This means that a small little 3-inch diameter telescope collects almost 100 times as much light as your eye does. So that means things will be 100 times brighter. And it'll collect that much more light. So this is one graphic example to tell us and remind us why we should never, ever look at the sun with a telescope or binoculars. The magnification and the gathering of the light from a telescope or even a pair of binoculars is enough to damage your eyes. The sun would appear 90 times brighter, and this would cause permanent damage to your eyes if you tried to look at the sun through a unfiltered telescope. Let's do another example of light gathering power. So telescope A here has a diameter of 90 centimeters. Okay, so this is a much larger telescope now, and the diameter of this telescope is 30 centimeters. So what is the light gathering power of telescope A compared to telescope B? So all we're doing here, again, we're gonna compare telescope A, its area, divided by telescope B area. And as we saw in the last example, all we have to do is take the diameter, 90, and square it, divided by the other diameter, 30, and square it. So this, we can do a little simplification here. We can cross off these zeros, so we get 9 squared over 3 squared, and remember we can put the 9 over 3 in parentheses, so we can actually do this one in our head. 9 divided by 3 is 3, and we have to square that to get a factor of 9 difference. So telescope A has 9 times the light gathering power of telescope B in this example. So in order to see what the effect of more light gathering power is, these are 3 simulated images. I actually took these images with the telescope that I built. I'm going to share that with you later on in this lecture. But these are pictures of a famous galaxy called the Whirlpool Galaxy. And this is what that galaxy might look like through a small telescope, through a medium telescope, and through a large telescope. So the main idea here again is with a larger telescope, we have more light gathering power, so the image appears brighter. The second power of a telescope is called the resolving power of a telescope. And this has to do with how much resolution or detail we can see in a telescope. And this has to do with the fact that due to the wave nature of light, the telescope itself produces wave interference, which are called diffraction rings around the image. So ideally, a star in an image would look something like this, a point of light, because the star is so far away. But if we actually magnify this image of the star many, many times, we would actually see that the star's light is spread out in a bunch of light rings with dark circles in between the rings. These are these so-called diffraction rings. And this has to do with the fact that the light is traveling through a circular opening in the telescope. We saw this effect of diffraction and interference in part 1 of this chapter. So what happens here is if we have two stars that are very close together in the sky in our image, these two stars may actually blend together through the telescope because of these diffraction effects. In other words, the telescope can now no longer resolve these two stars. They're sort of blurred together as a single image. So how do we get rid of this issue? How do we resolve this problem? No pun intended. Well, it turns out that the larger the telescope is, the smaller the diffraction rings are. So through a small telescope, a star's light is spread out more and blurred more. Through a medium telescope, less, and through a large telescope, the light is concentrated to a small region the way we want it to be. So here's another case where a larger telescope produces sharper images, more resolution, higher resolution, more resolving power. So here is a simulation of the effect of telescope resolution on an image. Again, these are images that I took with my home-built telescope using a digital camera, and this is a picture of what's called a star cluster, or a globular star cluster. Through a 6-inch telescope, a small 6-inch diameter telescope, the cluster might look something like this through the eyepiece. Notice that the stars are a little blurred, and also towards the center of the cluster, all the stars are just blurred together into one blob. And this doesn't mean that the image is out of focus. In fact, this is in focus. This is just the best image we can get from a small telescope because it doesn't have a lot of resolution or resolving power. Now, through a medium-sized telescope, notice the picture is markedly clearer. We have more resolution. But when we go to the full aperture, this is an 18-inch diameter mirror, which is in my telescope. Now we have the full benefit of the resolving power, and you can notice that the stars are small pinpoints of light, and if we look towards the center of the cluster, you can see individual stars now. They are resolved. So once again, we see that bigger is better when it comes to telescopes, not only for light gathering power, but also for resolving power. The third power of a telescope is the magnifying power. And a lot of people think that this is the most important power of a telescope, but it turns out that magnification is the least important property, and we'll see why shortly. But magnifying power is the ability of the telescope to make the image appear bigger. And in astronomy, obviously this is important because, again, a lot of the objects we're looking at are so far away that they would appear very small if we weren't able to magnify, which effectively brings the object closer. So it turns out that the magnification of a telescope depends on two things. It's the ratio of the telescope's focal length divided by the eyepiece's focal length. So magnification M is equal to F sub O, where the O is for objective lens. That's the primary mirror or lens of the telescope. This just tells us what the telescope's focal length is, F sub O. And then F sub E is for eyepiece. We need to know the focal length of the eyepiece lens. Now, one thing about this is that by changing the eyepiece we can effectively change the magnification of the telescope. So the telescope itself doesn't have an inherent magnification. It's the combination of the telescope with the eyepiece that gives us magnification. And one thing that's important here is that a larger magnification does not improve the resolving power of the telescope. So to see what this means, magnification does not improve image quality. So suppose you have a blurry picture of a friend. What happens if you try to zoom in or blow up this picture? Does it look better? Of course not. It actually looks worse with higher magnification because the image that we started with was poor quality. Here is a poor quality astro image or astrophoto of some stars. Notice it's blurry and out of focus. If we zoom in on this picture, it looks even worse, right? All the resolution is just not there. So magnification is not really that important. What's more important is how high of a quality the original image is, and that will be determined by the resolving power and the light gathering power of the telescope. We can always zoom in on an image later to see, to make it larger. So let's look at and see how the eyepiece size affects the magnifying power. So here's our equation again, or our formula for calculating magnification. For my telescope that I took these pictures with, it has a telescope focal length, the FO, of 2,050 millimeters. Now that's 2.05 meters, meaning it's about 6.5 feet tall. So I'll show you pictures of my telescope later, but I have a short step ladder that I have to stand on in order to look through the telescope in some positions because it's taller than I am. So that's going to be our number on the top. Now, suppose we start by looking at this star cluster with an eyepiece that has a focal length of 32 millimeters. So to figure out the magnification, we take this number, 2050, and divide it by this number, 32. Remember, we got FO divided by FE. And that gives us a magnification of 64 times. Now, what does that mean? Well, that means if we were to look up in the sky with our naked eye, all right, with our unaided eye, no telescope, this object would look 64 times smaller. So the telescope here is magnifying our view by a factor of 64 times, which is actually quite a bit. Most binoculars that you use magnify about 7 times. So this is almost 10 times more than that. But notice in this picture here, or this view through the telescope, the star cluster still looks kind of small. So what we can do is just remove this eyepiece from the telescope and put in a smaller focal length eyepiece. This one has 16 millimeters for its focal length. So now we have 2050 divided by 16, which is 128 power. So notice now the star cluster is twice as big as it was here, because we went from 64 times to 128 times. And we can keep going. Let's take out this 16 millimeter eyepiece and put in an 8 millimeter eyepiece. We're doubling the magnification again, and we're up to 256 power. So now it fills the frame and we can see the details in the object here. Now you might be wondering, why don't we just keep going? Can't we go to 1,000 times or 1,000,000 times even? Well, the problem is, remember, once we start magnifying too much, we start to lose basically information. We saw what happens if we take a blurry picture and we zoom in on it. It doesn't look any better. It starts to look worse. And so that's what happens with telescopes. On the Earth here, we can typically go up to maybe 300, 400, sometimes a little bit higher in magnification. With the Hubble Space Telescope up in space, it can obviously go much, much higher than this because it doesn't have to deal with turbulence in the air and other effects like that, which we will talk about later. I mentioned before that all of the professional observatory telescopes that professional astronomers use today are reflecting telescope designs, not refracting. That means they use telescopes with mirrors and not lenses to gather the light. So This is just showing kind of some of the various designs for mirror or reflecting telescopes. So in this one here, the large mirror is down here. It focuses the light, and the light would normally come to focus right about here. But the problem is, if you wanted to look at this image, you would have to get inside of the beam of incoming light, and obviously you would block the light from the telescope. So that's not good. So what Isaac Newton did, he came up with a clever trick. He put a secondary mirror right here at a 45-degree angle that reflects the converging light rays out of the telescope so they can be viewed over here on the side. Now later on, it was realized that this secondary mirror could actually shoot the light rays that are converging to a focus. It could shoot them out the back of the telescope through a hole in here. And interestingly, this hole does not disrupt the image or the view from the telescope. So most modern telescopes are built something like with this design here. Here's another one here. Here's the primary mirror down here. You can see it looks kind of like a donut with a hole in the center. And then here's a secondary mirror up here. So light comes in from the top, bounces off the primary mirror, hits the secondary mirror, and then comes out a hole, and the focus is back here behind the telescope, which is very convenient. So this is where you could either look through the telescope back here, or modern telescopes actually use detectors, cameras, and spectrographs, and those would be mounted behind the telescope here. Right here in our neighborhood in Southern California, up on Palomar Mountain, is one of the biggest telescopes in the world. In fact, the Hale telescope, the 200-inch telescope up there, was the largest telescope for almost 50 years. And so it's kind of nice that we have this historical, iconic telescope right here in our backyard, and you can go up and visit it, and you can either do a self-guided tour, or you can get in a tour group and they will take you inside. But you can, anybody can go inside the dome here and look through the window, look through the glass, and see this enormous telescope. To give you an idea of the size of this telescope, notice down here, this is a ladder. Right? This is a tall step ladder for someone to climb up in. So the mirror hangs down here, and it is a 200-inch diameter mirror, which is 5 meters or about 17 feet in diameter. And this thing is just enormous. And this structure here is the bearing, and this thing slowly rotates so that the telescope can track the stars in the sky. The secondary mirror is actually up here, which focuses the light out and back down through the primary, and then down here below the primary mirror is where the camera or the other instruments would be attached. And all of this is inside of a dome, which is seen here in this picture. So this is something that I would highly recommend going up to visit. And if it's open, you can get extra credit by going up there and making a visit to the famous Palomar Mountain telescope. And again, it's only about maybe a 40-minute drive from Cal State San Marcos. A couple of the other really big monster telescopes are the twin Keck telescopes on the top of Mauna Kea in Hawaii. And this uses a different design. This is a picture of the mirror when they were constructing the telescope. To get an idea of the size, again, here's a grown man inside the center of this thing. But notice the mirror is not a single mirror. It's actually made up of a bunch of honeycomb-shaped sub-mirrors that are all sort of tiled together to form this enormous mirror, which is 10 meters or 33 feet in diameter. And there's actually 2 of these telescopes on top of the highest peak on the big island of Hawaii. My family and I went up and visited them a couple years ago, and it was a really neat trip. It was 85 degrees down on the beaches. We were snorkeling, and we drove up to see the telescope, and it was 30 degrees. It was below freezing. But quite a trip to get to the top of the mountain, and an excellent place to build huge telescopes like this. The top of this mountain, by the way, is 14,000 feet in elevation. So some of the more modern telescopes They use some different technologies to make them better. One is what they call a floppy mirror. It's a thin mirror that is controlled by computer actuator, computer thrusters, basically computer controlled thrusters down here that can make minute adjustments to the shape of the mirror to keep it in perfect alignment. And these adjustments can be made hundreds of times per second. And then we just saw the segmented mirror approach, which is used by some of the largest of the telescopes. Regarding future telescope plans is kind of interesting, because remember, the idea here is that bigger is better. So a larger telescope collects more light, and it also has higher resolving power. And so there's sort of a race going on to build the biggest and best telescope. So one that's under construction right now is called the TMT, or 30-meter telescope. So remember, we're talking about a 30-meter diameter telescope. So the 30 meters is about the third of the length of a football field. Here's another one, the ELT, which stands for the extremely large telescope. The plan for this one is a 42-meter diameter primary mirror here. The Euro 50 is a 50-meter diameter telescope. So here's a mirror that is half the size of a football field. And one of my favorites, the OWL, the OWL, which stands for Overwhelmingly Large Telescope. So here, this is just in the planning stage. They're not even sure how or if they can build this thing. But the plan is to have a 100-meter diameter mirror. And this mirror has to be kept to a precision of a millionth of an inch. And so the technology to build and operate something like this is really beyond what we have right now. But hopefully in our lifetimes we'll see the construction of something like this. One thing that is basically going to happen very soon is the James Webb Space Telescope is going to replace the Hubble Space Telescope. And the James Webb has a mirror that's 6.5 meters. Now that's not huge by today's standards, but remember, this is going to be up in space. The Hubble, for comparison, is 2.4 meters, and the Hubble is arguably the most powerful telescope ever built. So this one has a diameter of about 3 times as much as the Hubble, meaning it has the light gathering power of almost 10 Hubbles. And so there's been some delays in the construction and the deployment of this telescope, but the current plans are to have it launched in 2021. So the whole astronomy community is anxiously awaiting the James Webb Space Telescope to see what it can discover. One of the biggest or big parts of the whole study of astronomy is how do we capture images and take pictures with these powerful telescopes. And of course, everything today is all the imaging is done digitally, but that's been quite an evolution. For example, back in the 1800s, before cameras were even invented, astronomers had to make sketches of what they saw. So this is a sketch from 1845 of the Whirlpool galaxy. In the late 1800s, photography was invented, and astronomers started to use film cameras for astrophotography. So this is a black and white photo from 1955 through a telescope of the same Whirlpool galaxy. And then in the 1980s, there was a revolution in imaging when digital cameras started to replace film cameras. And the advantages are that the digital cameras are much more sensitive than film cameras, and they allow image processing techniques to enhance the images. So this is a modern image of the Whirlpool galaxy taken through a modern digital camera. So the whole concept of digital imaging has to do with pixels, which you've no doubt heard of. Then the word pixel comes from picture element. And if you were to look inside of a digital camera, even including the one in your smartphone, there is a little chip in there, a little electronic chip that is called the camera detector. and it has an array of kind of like a checkerboard, rows and columns of pixels. And each one of these little squares here is a pixel, which is a light-sensitive photodetector that converts light energy into electricity. So basically, these pixels convert the light that falls on them, it converts them into an electrical signal that can be processed. So if we look at a digital picture like this, a black and white picture of the butterfly, and if we zoom in on the butterfly's head enough, we can actually start to see the pixels in the image that make up this image on the left. So the pixels allow the image to have resolution. So the basic idea is that more pixels provide better resolution or detail. So modern cameras for astronomy, or even digital cameras that you buy off the shelf, contain millions of pixels, and those are known as megapixels. Remember, the word mega means million. So if your camera is a 6 megapixel camera or detector, that means it has 6 million of those pixels in rows and columns on the detector. And ideally, the camera resolution will match the telescope resolution. Just to show the effect of adding more pixels, this diagram down here shows what an image would look like with 1 pixel. Obviously, there's no detail at all here. All 1 pixel would show is the average brightness of the image. This is 4 pixels in a 2 by 2 array, so 2 rows, 2 columns, and obviously we still don't see any detail here. Going to 5 by 5, that's 25 pixels. Now we can see that there's something bright in the center, but obviously we don't have enough resolution yet. When we go to 10 by 10 or 100 pixels, we can start to make out the rough shape of the object, but it's still too pixelated to be able to really tell what's going on. This is 20 by 20. This is 50 by 50, and by the time we get to 100 by 100, this is 10,000 pixels. The image looks pretty good, right? It's hard to tell unless you maybe magnified this image. You wouldn't be able to tell that there are individual pixels in there. So this is only 10,000 pixels. So again, most modern cameras have millions of pixels. One of the challenges for astrophotography and for astronomers that are taking images in space is something called the signal-to-noise ratio. The signal, signal is the good stuff. That's the information which is desirable from the object being imaged. And the noise is the bad stuff. Those are random variations in the signal due to a combination of factors such as light pollution, interference, even heat produces noise, thermally produced electrons, etc. So to have a good image, we want a lot of signal and we want very little noise. And that's normally not a problem if you're taking pictures in bright daylight. But when we're doing astrophotography, when astronomers are taking pictures, the signal is always very weak because they're looking at far away, very faint objects at night. So the noise can actually be greater than the signal. So this is an early image that I took many decades ago with an early digital camera. Actually, this was one that I built myself. And this is called the Horsehead Nebula, which is a very faint object. And this picture is of poor quality because it has a low signal-to-noise ratio. In other words, the signal is weak and the noise is strong. So the result is a grainy, poor image. This is a different image of the Orion Nebula that has a high signal-to-noise ratio. The result is a clear, detailed image. So how do we get a higher signal-to-noise ratio? Well, the answer is longer exposures. If we take a longer exposure, meaning we leave the camera shutter open, allowing it to collect more light, then we can build up the signal over time, and the noise is random, so it doesn't build up as fast as the signal. So when you take a picture with your smartphone in bright daylight, the exposure is probably, I'm guessing, maybe 1/60th of a second, maybe even less. It's just a tiny fraction of a second. When astronomers take exposures at night, The exposure times range from several minutes to several hours. So look at these pictures here. These are two pictures that I took of our nearby neighbor, the Andromeda Galaxy. This picture on the left has an exposure of 8 minutes, which sounds like a lot, but it's not in astronomy. So notice the picture here has a bunch of artifacts. It has these streaks or stripes going across the picture. That's due to electronic noise in the rows and columns of pixels. But look at this picture on the right. This is a total exposure time of 40 minutes. The noise from those streaks is basically gone, and notice how much clearer and more detailed the picture is because it has a higher signal to noise ratio. One of the other challenges for astronomy and taking pictures through telescopes is the effect of light pollution. Light pollution is due to city lights. This is man-made lights due to cars, street lights, porch lights, industry, any source of unnatural light we call light pollution. And this causes sky glow. And so that's basically a type of noise. And so light pollution reduces the signal to noise ratio. So here are some pictures of a galaxy that I took. This was from my backyard in Carlsbad, and I took this on what I thought was a very dark and clear night. But the exposure here, what happens is, remember, we're doing a long exposure here of several minutes. The sky glow is building up just as fast as the picture of the galaxy is. So instead of seeing a nice dark sky behind the object, which is what we want, we're seeing all this light pollution, and it makes the sky look sort of brown or even orange. All right, so it's horrible. Now, look at this picture I took up on Mount Laguna. These are the local mountains out to the east of San Diego, up about 6,000 feet in elevation. Out there, there's very little light pollution. The skies are dark and clear. And so here you can see, the galaxy picture here is much, much better because of the lack of light pollution. Notice how dark the sky is behind the galaxy. That's what we expect to see in an astrophoto. This is a satellite image of the United States taken at night, which helps map out where all the regions of light pollution are. So we can see in all the major metropolitan areas, New York City, here's Chicago, and then in California we can see this is San Diego down here, this is Los Angeles and Orange County, and then this is the Bay Area up here. So there's good news and bad news for us in Southern California here. The bad news is the light pollution is horrible along the coast in Southern California due to all the cities. But notice if we drive east, notice how dark it is just to the left of San Diego in this map. This is our local deserts and mountains out east, and they're actually very dark. So you don't have to drive far. You can drive an hour or maybe 2 hours at most and be out in extremely dark skies and enjoy the dark sky the way they are supposed to look. One of the other challenges is the effects of the atmosphere. On a hot day, you've probably seen the air shimmering above maybe a parking lot or even above the top of your car. This is due to the thermal effects of convection currents, of warm air rising up and causing the shimmering kind of blurring air, and the air becomes very unstable. So at sea level, an image like this might be typical due to the poor seeing effects of the air. But if you get up in the mountains in high elevation, you're basically above a lot of that thick shimmering air, and the image is much clearer. So the best locations for telescopes, we want to avoid light pollution, so we need a dark site, and we want to avoid the atmosphere, meaning we want to be high up on top of a mountain. So the top observatories that are built today are out, at remote places on top of mountaintops. So the ESO, the European Southern Observatory, has a few observatories and several telescopes on top of the Andes Mountains in Chile. And here's another one of their observatories here. And so these are high up, remote places. They're dark, they're isolated and desolate, and because of their altitude, they're far above most of the Earth's atmosphere. These are the Keck telescopes again on top of Mauna Kea, 14,000 feet above the Hawaiian coastline. And again, this is it's very dark and high up here. The ultimate place for a telescope is, of course, in space. Up here, there's no light pollution at all, and obviously there's no atmosphere, so we don't have to worry about that. The problem is it's very expensive to launch and maintain telescopes in space. But we'll learn a little bit more about the Hubble Space Telescope soon. Telescopes have been designed to allow us to see the universe across the entire electromagnetic spectrum. So remember what we learned about the electromagnetic spectrum is that the visible light that our eyes can see is only one tiny sliver of the whole spectrum. So most of the universe is invisible to us, but we can build telescopes that are sensitive to different parts of the spectrum to allow us to see the invisible universe. So it's a pretty amazing technological advance to be able to have telescopes that not only allow us to see in the visible light spectrum, in other words, how our eyes would see it, but also we can have telescopes that are designed to see in infrared, in ultraviolet, in radio, in X-ray, and even in gamma ray. So we're going to look at some of these different types of telescopes in the next few slides. This, by the way, is a picture of the famous Hubble Space Telescope. It's about the size of a large bus, and this is the aperture door, basically, which is opening. So light is coming in from here, and the mirror of the telescope is back in here somewhere, and all the instruments are packaged behind it. So let's go through some of the portions of the electromagnetic spectrum and see how telescopes can basically exploit the different parts of the spectrum to see different things. So we'll start with radio astronomy. So this is, again, what's shown here is the electromagnetic spectrum. And this little sliver here, what says visual, this is, again, what our eyes can see. These are the colors of the rainbow. So if we go beyond the red here, we're in the infrared region, and if we keep going past infrared, we're in the microwave region of the spectrum. And if we keep going all the way to the end, this is the radio portion of the spectrum. These are radio waves. And, of course, we use radio waves for our car radios, as an example, AM or FM radio. And even television, especially in the old days before cable, television used the sort of upper end of the radio spectrum here for UHF and VHF communication. So radio telescopes are going to see light, basically, in this portion of the spectrum. They're able to image in the radio wave portion of the electromagnetic spectrum. So here is a picture of a galaxy seen in both visible, which is the white portion here, and in radio waves, which are the purple clouds here. So in order to understand this image, it's basically two different images superimposed on top of each other. So the background image is the visible light image taken. This is what our eyes would see through a telescope. This is a galaxy. This fuzzy blob in the center is a giant swarm of billions of stars, just like our sun. And what's not seen in visible light are these jets shooting out from the center of the galaxy and producing these lobes. These are called radio lobes that are glowing and giving off radio emissions. So these are completely invisible to our eyes, but a radio telescope can see them, and astronomers can study these structures that are, and this is actually energy shooting out from a black hole in the center of this galaxy. So what is a radio telescope? Well, it's basically a large dish. Here's a picture of one here that focuses incoming radio waves. The dish, the bowl shape of the dish, focuses these radio waves to a focus up here where there is an antenna that picks up the radio waves and sends those electrical signals to, it might be an amplifier, and then finally a computer is used to produce an image of the radio signals that are coming in. One of the nifty tricks of radio telescopes is that they can be connected together to form an effectively huge telescope. And this is called interferometry, where we connect different telescopes together to make a bigger one. This is a famous interferometer radio telescope in New Mexico. It's called the VLA, or Very Large Array. It's 27 individual radio telescope dishes, and these dishes individually are huge. Notice you might be able to see in some of these pictures cars on the road here, but these are large dishes, and they can be combined electronically to simulate a single radio telescope dish that's 36 kilometers in diameter. That's about 20 miles. So these things can be moved apart a total distance of something like 20 miles. And by moving them apart, remember, we can get more resolution, because bigger telescopes mean more resolution. This is a radio telescope image of the Whirlpool galaxy, showing what it looks like in radio waves. And by the way, speaking of interferometry, they've been able to, radio astronomers can even connect radio telescopes from different continents together and create basically a telescope the size of the Earth. These are some of the largest single radio telescopes. In Puerto Rico, there's a 300-meter diameter dish. So again, the size of this thing is more than 3 football fields in diameter. China has recently built one even bigger than that, the 500-meter radio telescope. And in Russia, there is a radio telescope. Instead of a solid dish, it's a ring that has a total diameter of 600 meters. So these are enormous observatories. Now, one of the advantages, well, there are several advantages actually of radio telescopes. And one of them is, if you think about radio waves, you can listen to a radio when you're inside of your house. You can use your cell phone when you're inside of a building, and you can actually send text messages or talk to someone on the phone that is outside of the building. Now, how is that possible? Well, the radio waves actually go right through the wall. So radio waves penetrate through not only walls, but for astronomers, radio waves penetrate through dust and gas clouds, allowing them to see regions of space that are blocked from view in visible light. So this is another way that radio telescopes allow us to see the invisible universe, or the hidden universe. We can actually see through objects in radio. The other thing I'll mention here, we already just talked about actually, is that by connecting radio telescopes together, we through the process called interferometry, we can basically achieve very high resolution imaging by effectively making a larger radio telescope. So radio telescopes, one nice thing about them is that radio waves penetrate through our atmosphere. So radio telescopes can be built on the ground. But some of the other parts of the electromagnetic spectrum, like the infrared, the ultraviolet, the X-ray, and the gamma ray, most of these photons are absorbed by our atmosphere. And as a result, we can't build telescopes for IR, UV, X-ray, or gamma ray. They can't be built on the surface of the Earth. They have to be placed in orbit. So we're going to now look at astronomy from space. There are obviously many advantages of having a telescope up in space. One of them being no light pollution, the other one no atmospheric turbulence or blurring, so the seeing is perfect in space. And then of course we have access to these other rays here that are absorbed by our atmosphere. So infrared astronomy, remember infrared is heat energy that reveals temperature variations that are invisible to our eyes. So if we were able to look at a person holding a match in infrared, they might look something like this. So with infrared vision, we could see in the dark. We could see warm objects glowing by the heat that they give off. And of course, our eyes aren't sensitive to infrared, but it's easy to make infrared cameras that are sensitive to infrared. So this is a a star-forming region. This is a cloud of gas and dust where new stars are forming inside of it, and this is seen in infrared. So we're looking at this with wavelengths that our eyes would not see, and we're seeing variations in the temperature of this giant gas cloud. One of the most powerful instruments for infrared astronomy was NASA's Spitzer Infrared Space Telescope, and these are some of the images that it has taken in the infrared. And again, this is a satellite telescope that is orbiting around the Earth and shooting the universe, basically shooting photography in the infrared. Let's move on to the ultraviolet portion of the electromagnetic spectrum. So UV rays trace hot objects. It takes a lot of heat to produce ultraviolet. So these objects have temperatures greater than 10,000 degrees. Again, because most ultraviolet is blocked by our atmosphere, which is a good thing, UV telescopes have to be placed in orbit. This is an example of a galaxy, this galaxy called M81. This is what it looks like in visible light. This is the same galaxy imaged in ultraviolet light. And so what astronomers are seeing here are some of these star-forming regions in the galaxy glow because they give off more ultraviolet than other regions. Our next stop in the electromagnetic spectrum for astronomy is the X-ray portion of the spectrum. So telescopes such as NASA's Chandra X-ray Observatory were designed to image the universe in X-rays. And again, these telescopes have to be placed up in space because X-rays are eventually absorbed by our atmosphere. X-rays are produced by very hot million-degree gas. Some of the sources of these X-rays are exploding stars, neutron stars, and black holes. And this is an image here. This is the remnant of a star that exploded, that blew itself up. This is called a supernova explosion, and this is what it looks like in X-rays. So if you had X-ray vision, this is what you would see from a star that has blown itself up. And we'll talk about supernovas later on in the course when we study astronomy. The highest energy photons in the electromagnetic spectrum are the gamma rays. And gamma rays are produced by some of the most violent processes in the universe: exploding stars, black holes, and radioactive decays. There have been a couple gamma ray observatories placed in orbit. This is the Compton Gamma Ray Observatory, and this is the Fermi Gamma Ray Telescope before it was deployed, and it's in orbit now. And this is showing this is kind of an interesting picture here. This is a picture of our Milky Way galaxy here from Earth, taken from Earth. But what they discovered with this Fermi Gamma Ray telescope was that our galaxy is blowing bubbles. And these enormous bubbles here are gamma ray emissions. And this was a fairly recent, something found, fairly recently, and certainly in the last 10 years or so. This was unknown before because, again, these gamma rays, remember, are invisible to our eyes. But these bubbles are huge. You can see they, from the top here to the bottom, is something like 50,000 light years in distance, and a single light year is about 6 trillion miles. So these are enormous structures of gamma ray bubbles emerging from the core of our galaxy. And the thought is that these gamma ray bubbles are coming from the supermassive black hole in the center of our galaxy. So this is something that we'll learn more about later in the course, again, when we talk about astronomy. The Hubble Space Telescope is probably the most famous telescope that was ever built. It was launched in 1990, which is 30 years ago, and still in use today. It orbits about 350 miles above the Earth, and it is arguably the world's most productive science instrument. It has produced more than 500,000 images of our universe, and more than 9,000 research papers have been published using data taken from this telescope. So it's been an extremely important asset and tool to professional astronomy and our understanding of the universe. One of the one of the many pictures that the Hubble has taken was called the Hubble Deep Field Image. Let's go ahead and watch a video clip that will explain and show some of the results of this amazing Hubble Space Telescope image.
Have you ever wondered how big the entire universe is? The visible universe is unimaginably huge, but there is one image that can give us a small glimpse at its awe-inspiring scale, and that is the Hubble Deep Field Image. In 1995, astronomers wanted to see what would happen if they pointed the new Hubble Space Telescope at an area of the sky that was nearly devoid of all stars. They let it soak up light for over 140 hours over a span of 10 days, and what they saw was nothing short of spectacular. This is the Hubble Deep Field Image. What you're seeing here is not just a few stars, nebulas, and star clusters, but each and every dot and fuzzy patch you are seeing is an entire galaxy, each containing around 100 billion stars. To get an idea of how many stars are in each one of those galaxies, imagine an Olympic-sized swimming pool and fill it with standard 1.5 centimeter marbles. If my calculations are correct, taking into account the max density of close-packed spheres, it would fit around 1 billion marbles. That would mean we need 100 Olympic-sized swimming pools full of marbles to equal the number of stars in an average galaxy. In a similar, more recent capture called the Hubble Ultra Deep Field Image, we can see around 10,000 galaxies, each with around 100 billion stars. Pretty cool, right? But you haven't heard the most amazing thing yet. This image is not the entire sky, far from it. This is only a tiny fraction of the sky, 1/13 millionth to be exact. Look at the size of the D on the front of an American penny, then hold the penny up to the sky at arm's length. The area of the sky that the Ultra Deep Field Image takes up is roughly contained entirely in that tiny D. The Hubble Deep Field Images allow us to peer deeper into space and time than we have ever seen before. I say deeper into time because some of these objects are so far away, the light coming from them has taken up to 13 billion years to get to us. So we're seeing them as they looked less than 1 billion years after the Big Bang, long before the Earth was even formed. Some of these distant objects are called quasars, which are the most powerful and luminous objects in the universe. Even though they're only about the size of our solar system, they emit up to 1,000 times more energy than the entire Milky Way galaxy, which contains between 200 and 400 billion stars. They're made up of supermassive black holes that are consuming so much material that they shoot giant jets of particles traveling at nearly the speed of light, thousands of light years into space. Yeah, quasars are pretty awesome. Looking at this image is a humbling experience, but to me it just shows how amazing our universe is and how much there is left for us to explore. It's almost unfathomable that we could be the only life in this vast universe. Peer into this image long enough and you'll start to imagine what awe-inspiring wonders could be hiding in those distant galaxies full of billions of planets. Scientists are learning more about our universe and our local galaxy every day. Just imagine what they might find next. You can download a high-resolution copy of the Hubble Ultra Deep Field Image here, or on the link in the description below. If this is your first time on our channel, I hope you'll subscribe to catch more of our upcoming science videos, and also check out some of our educational videos for preschool kids. Thanks so much for watching, and see you next time!
All right, now that we're back down to Earth, I wanted to just briefly share with you my telescope that I built. This is a home-built 18-inch reflecting telescope. So what 18 inches means is that the mirror, which you might be able to see down in the bottom of this box, the mirror is 18 inches in diameter, and the mirror is about 2 inches thick, and it weighs about 50 pounds. So the mirror itself is a very heavy piece of glass. I built the rest of the telescope around the mirror. I bought the mirror from a professional mirror making facility, and then built the rest of the telescope around it. So it has computerized tracking, and so I can basically dial in any object or position in the sky that I want, and the telescope will automatically move to that object and then start tracking it. The total cost of this project was about $8,000, and as they sometimes say, hobbies are a good way to waste time and money, and that was certainly the case for this telescope. I thought I would just show you some of the pictures that I've taken through my various telescopes, and these are with a digital camera mounted to the telescope. And so this picture here I actually took through a much smaller telescope, an 80mm refractor. This telescope's only about 3 inches in diameter, but it takes very nice pictures of large sort of diffused objects that take up more of the sky. This is the famous Orion Nebula, which is a giant cloud of glowing hydrogen gas. And what's happening, we'll learn more about this when we study astronomy later, but this is the birthplace of new stars. This is a picture of the Andromeda Galaxy. And again, I took this with a very small telescope using a digital camera mounted on the back of the telescope. And this Andromeda Galaxy is similar to our Milky Way galaxy. It contains, we think, about 400 billion stars. Remember, each of those stars is a sun, like our own sun. It's about 2.5 million light years away. Now remember that the speed of light travels 1 light year per year. So that means it took the light from this galaxy 2.5 million years to get to Earth. So in a sense, telescopes are time machines. When we look through a telescope, we're looking back into the past. This is what the galaxy looked like 2.5 million years ago. And astronomers have built obviously much more powerful telescopes than this, allowing us to look back billions of years into the past of our universe's history. This is a famous star cluster called the Pleiades. It can be seen on fall or winter evenings in the sky, and around the bright stars, the ancients called this the Seven Sisters. But this nebulosity or glowing wisps of gas are what's left over from the basically the birth of these stars. It's leftover material from the cocoon that formed these stars. And by the way, the blue color of this nebula, it's the same physical process that makes our sky blue. It's starlight scattering off the gas. This is a favorite object that a lot of amateur astrophotographers like myself like to photograph because of its bright colors. This is the Trifid Nebula. And again, what we're seeing here is a large collection of mostly hydrogen gas, but we can also see dust clouds. And this is another stellar nursery, they call it, where new stars are being born. And this picture and the ones that follow were taken through my home-built 18-inch telescope. And I used a Canon digital camera connected to the telescope. Here was a comet. Now, this is not the recent comet that just visited Earth. This one was back in 2006, and I took this up on Laguna Mountain. And this comet was not nearly as bright as the one that you may have seen this summer. This particular one could only be seen through the telescope, but you can see the head of the comet here, the nucleus, and you can see the tail extending upwards. Here's another, this one is called the Dumbbell Nebula. This is the result of a star that is basically dying and casting off its outer layers of gas. This was taken again with my 18-inch telescope, and this was with a different digital camera that was designed for astrophotography. Here's a picture of a globular star cluster called M22. This cluster contains about 100,000 stars that are like a swarm of bees. They're basically connected or bound together by their own gravity. Each one of them is sort of randomly orbiting around the center of gravity of this system. And these are extremely old stars, something like 10 billion years old. Here is another nebula called the Lagoon Nebula. Again, this is a giant cloud of glowing hydrogen gas. The gas is glowing by a process called fluorescence, which is actually similar to the way a fluorescent light bulb works. We'll learn about emission nebula like these later in the course, and we'll talk a little bit about this in the next chapter when we discuss how atoms work and how atoms produce light. Again, these nebula are birthplace of new stars. So these bright stars that you see in the image here are relatively young stars. They're probably less than 1 million years old, and they were formed from the gravitational contraction of all of this gas and dust. So this single giant cloud may produce hundreds or even thousands of new stars. Here's another galaxy called M81. This is a spiral galaxy, sort of like our own Milky Way galaxy. This particular galaxy contains hundreds of billions of stars, each star like a sun, just like our own sun, with planets. It's approximately 12 million light years away. So remember again, what that means is we're looking back in time 12 million years. That's what this galaxy looked like 12 million years ago, because that's how long it took that light to reach my camera. This is just one of more than 100 billion galaxies in the known observable universe. Now, here's another picture of a galaxy. This is called M101, and it's not a great picture because this galaxy is very faint. However, the reason I wanted to show you it is this galaxy has an exploding star here. This is called a supernova, and this star was detected back in September of 2011. So I took my telescope up to Laguna Mountain and photographed the galaxy so I could see this supernova. Now, there's a couple interesting things about this. First of all, when a star blows itself up like this to make a supernova, it outshines the entire rest of the galaxy, which has 100 billion stars. So that gives you an idea of the power of this explosion. By the way, these other bright stars that you see in the picture here, these are all foreground stars in our own Milky Way. So we're actually looking out of our galaxy into deep space to image this galaxy M101 in the distant background. But this star here is not a foreground star. This is part of this galaxy system, and this star exploded. Now, the other thing that's interesting about this is, remember, I took this picture back in 2011 when they discovered this supernova. But when did this supernova really explode? Well, this galaxy has a distance of 27 million light years. So that means this star actually blew up 27 million years ago and was just detected recently because it took that long for the light to get to us. So again, that's part of this fascinating concept of space and time. When we study the universe, the farther we look out into space, the farther back we look in time. And we will exploit this interesting phenomena in astronomy because we can learn about our past by looking farther out into space. The last image I'll share with you here is another picture of the beautiful Orion Nebula. This was taken with a different camera, but again, this was taken from my 18-inch homebuilt telescope. And you know, the colors are just beautiful in this nebula. It's a bright glowing cloud of hydrogen gas and dust, and we'll learn more about the physics of why the hydrogen glows like this. We'll learn about that in the next chapter, and also when we study astronomy in a little bit later in the course, we will learn about the significance of these nebula and how they produce new stars. So that's it for this chapter. I hope you enjoyed seeing some of my pictures. I enjoyed sharing them with you, and I will see you in the next chapter shortly. Goodbye.